So howdy ho everybody, and thank you to listen my lecture on section 4.3 thermal conductivity in the course of solid state physics. So what we will do in this lecture is that we will look into the thermal conductivities of solids, and then I will show how the thermal conductivity of kappa is defined. So that's the main material parameter that is describing how well or how poorly a material conducts heat. And then we will talk of different lattice contributions that affect this conductivity of solids, so thermal conductivity, and we will show and discuss how phonons, so these lattice vibrations, and how defects, lattice imperfections are seen to play an important role in this process of thermal conduction. And instead of rigorous calculation-based approach, we will here really provide more of a phenomenological treatment, so that we just go through the main things that affect, but do not try to calculate things from ab initio, so not from the microscopic description of solid. So this is what we will do in this lecture. So we will start by just introducing to you the thermal conductivity as a material property, and then we will discuss the implications in terms of realistic materials. And here, we will basically start by progressing forward of the calculations we just made in the previous lecture. So we just have previously calculated the Debye heat capacities. So we introduced to you the Debye model, and now we will extend that treatment to also thermal conductivity. And in particular, we want to focus to understand how thermal energy is being transported in a solid as lattice vibrations. And I do not remember where we will mention this, but of course, thermal energy can be transported in a solid also via charge carriers, and so essentially when electrons can move in a piece of a solid, they can also transfer thermal energy from point A to point B, and this is of course an important process and mechanism in solid metals and in semiconductors, but here we are really more focusing on dielectrics. And from thermodynamics, we really remember that the transferred thermal energy, that's known as heat. So the parameter that describes heat is the capital Q, and then the material property that is associated with this process is known as the thermal conductivity, and the symbol is kappa. And although this above treatment of phonons and how we used the Debye model to calculate the heat capacity, although it gives us a good agreement for some of the materials, we must note here that the heat capacity C is not thermal conductivity, so that there will actually be also other matters that play a role in a thermal conductivity of a solid. So let's, for example, elucidate this by providing a practical example. And you know my fetish towards diamond. So that's my favorite material in terms of solid state physics. And it's among my favorite top 5 materials in general. Diamond has a very surprisingly small heat capacity C at room temperature. So really abnormally small. And the Debye model, for example, cannot really predict the heat capacities that well. Why this is so is that the lattice is really too stiff. Or let me rephrase. The diamond heat capacity does not yet approach the Dulong-Petit values at room temperature values. So it's rather way lower than what one would expect for materials that are at room temperature. And the reason for this is that the lattice is too stiff. if you look at the dispersion relation of a diamond and you look at the phononic dispersion relation, since we're speaking of thermal properties here, then you notice that the y-axis that gives us the energies of phonons, the y-axis is quite large in their values. And this means that when we are in room temperature, the phonons are mostly still frozen out, so to speak, so that the higher energy phonons are not yet excited. And because of this, the diamond lattice cannot yet store that much of thermal energy. And this really arises from the fact that the lattice is too stiff from the mechanical point of view. And this, of course, is related to the microscopic diamond structure and, of course, to the bonding between carbon atoms. But on the other hand, and this is why diamond is among my favorite materials, that it has an amazingly high thermal conductivity. And this is in terms of values, the kappa is around 2300 watts per meter per Kelvin at room temperature. And this is among the highest of values that is being found on materials. And this is for a normal diamond. And this value can be increased even further if you would impurify the diamond. So if you would make isotopically pure diamond, then the values would even be increased. And if you would go to lower temperatures, the heat capacity, the thermal conductivity of diamond would even increase. And why this is so is that the lattice is very stiff from the mechanical point of view, and this affects how easily or how quickly the phonons, the lattice vibrations, can propagate in the diamond lattice, and this increases the thermal conductivity kappa values. So I hope this elucidates a little bit that even though heat capacity plays a role in formation of thermal conductivity, kappa values of solids, it is not the only property that matters, and there are other things on the plate here. So we have really entirely neglected contributions from free electrons, and this is already what I mentioned earlier in the last slide, and this contribution is actually important in metals, and this will be discussed in the next chapter, where we are generalizing the classical Trude model into quantum mechanically correct treatment. So we will then introduce to you the Trude-Sommerfeld model, and once we have done that, we will also briefly discuss the contribution of free electrons, of conduction electrons in a metal and in a solid to the thermal conductivity. But more on that later in the next chapter, where we are, on the other hand, more focusing on the electronic properties of solids, but also a little bit of the thermal properties. So luckily, what we have in terms of the different contributions to the thermal conductivity kappa, they just add up. And why I'm saying luckily here, or writing in hyphens, is that of course, what happens is that we should resort into statistical analysis, and then the different processes that affect due to the statistical nature, then this implies that then the mathematics, instead of the kappa values, is that we just sum over different terms. So this is arising from the fact that we are using a statistical treatment on our system, and this is the kind of what gives us to this simple way of just adding up the different contributions. So the total thermal conductivity of a material will be Kp. So that's the lattice contribution, phonons, and then the Ke, where E is the contribution from free electrons, conduction electrons. So this is one way of calculating the contribution. The total thermal conductivity kappa, if you would know both of these contributions. And please note, these contributions, they are temperature dependent, and of course material dependent, and depending on the different temperature regime where we are, the results may be different. So the different contributions may dominate at different temperatures. maybe I should hammer down to my student the fact that we should really maybe consider using diamond in our research by in the next group get around we have that I will just play non-stop some diamond related songs. So I will make a playlist on diamonds, diamond songs. So I guess I will just mainly have a single song in that playlist. So the diamonds are forever from the classical James Bond movie. So let's see if he gets my point. I'm that kind of guy. So next, sorry about this, but I could not help myself. We will next proceed to just quantitatively a little bit more define our terminology, and I will just note that the formal treatment will be beyond our current scope. So I think it's perfectly fine that we are being phenomenological here. Just provide you a rough understanding, and I hope you are okay with that. So we consider a solid, and we are considering just a length of L, so or delta X length of a solid, and we have a cross section A, and we sandwich this between a hot and a cold thermal environment. So this is shown in the figure here. So we essentially have a conducting solid, and we want to understand how well this solid conducts thermal energy. So that kind of conduction is being scrutinized here, and we have the length L delta X here, and we have a cold environment associated with temperature T1, and here we have the hot temperature, and that's associated with temperature T2, and then we will have a change in heat so that the heat will flow in from the hot environment to the cold. And here is the cross-sectional area. For simplicity, we just consider some kind of rectangular object here. And now we want to understand how well this piece of a solid transfers thermal energy, and that's it. And in terms of applications, of course, in many different applications, we want to, for example, cool down our devices, or we want to heat up our devices. So this is where we are interested in thermal conductivities of solids. And we now define the way, how do we define kappa? So we start by just saying that we have a flux of thermal energy J, and E as in energy, thermal energy, and it's a vector. So in principle, we should take into account the fact that the heat is flowing in a given direction. So it's a flux and not a scalar valued quantity. And we assume that this flux is constant over the cross-sectional area A. So we do not care of the fact that maybe on for example, if you would have a small wire, maybe in the inside of the wire, the inner portions of the wire, the thermal conductivity would be slightly different than on the outer portions. So we just entirely neglect these possibilities. And then we can write that we have the capital JE. That's the kind of like total amount of thermal energy being transported. We can integrate that, or flux that we can integrate then over the cross-sectional area A, and we integrate over the flux of thermal energy J, and then we take the dot product with the differential of the surface. And of course, this notation means here that in fact we will need to define a surface normal with respect to this area A, and then we can proceed with the calculation. So please note what the notation means when we are performing a area integration over area, and when we must really define also the integral with respect to the surface normal. So this, of course, the integrand will be equal to taking the dot product of the flux of thermal energy J with the n hat. So that's the normal vector with respect to the surface A, and then we can have a scalar valued area differential dA, and now we can actually perform the integral more easily. And then if we have assumed that J is constant with respect to A, what comes out is that we really have just the area A times J, amplitude of the J. And this is now our change of heat with respect to temperature. And now we can define with this at hand the thermal conductivity kappa, And this is essentially the Fourier's law for heat conduction. So Fourier was looking into heat conduction quite a bit back in the days, and subsequently he developed the concepts of Fourier series and Fourier transforms as a neat way of calculating those differential equations. So now we can define thermal conductivity kappa, and that's defined that we have 1 over A, the cross-sectional area, times the partial derivative of heat with respect to temperature. So that was our J here. And we define that this must be equal to some kind of constant kappa with respect to the derivative of temperature over x. So maybe in three-dimensional sense it's better, and this is the one that is more known as the Fourier's law for heat conduction, that we have the flux of thermal energy J vector, and then we relate that we define that this must be equal to minus kappa times the gradient of the temperature. And this is known as the Fourier's law for heat conduction. So let's now look a little bit on this, because it might not be entirely transparent what we have here. So we have a kappa here, and we want to come up with a means to define that via some kind of equation. So here what we have is that we have a flux of heat, and how if we have a given like for example, or we have a given temperature difference between the cold and hot environment. So essentially we have some kind of temperature gradient through the solid we are looking at. And if we keep that constant, depending on how well the material conducts heat, thermal energy, so how large is this kappa value, then we will have a different amount of flux of thermal energy. So depending on how well the material conducts heat, then we will have a different amount of heat being transferred from the hot environment to the cold environment. So isn't this what this equation tells us? And this is what we are using to define what happens here. And if we have a larger temperature difference, then we will have a larger flux. And this seems to make sense intuitively, that if there's a larger difference between the hot and cold pool of environments, then the amount of thermal energy flowing will be different. And this is a way how we define kappa. Of course, we could just define the kappa is a minus of J divided by the gradient of temperature. And in this way of defining kappa, we would see that if we have the constant J, and if we then change the temperature gradient, then the K will change accordingly. And then here in a 1D case, maybe it is easier to understand, or maybe it's not. We, instead of calculating the gradient of temperature, we are just calculating the 1D gradient. So we calculate the derivative of temperature T with respect to the length variable x. And now we essentially just have made a 1D version of the Fourier's law for heat conduction. And that's the way we will proceed in our treatment. So this is how we define thermal conductivity kappa. And now the problem is turned into finding the kappa or some kind of relation of kappa with respect to some parameters that would it could be calculated from the microscopic point of view of a solid. So for example, we would want to relate somehow this thermal conductivity kappa and the lattice contribution. For example, with some parameters we could calculate using phonons and treatment we have developed so far for phonons. And the calculation of kappa from the first principles really would require knowledge of statistical physics and the kinetic theory of gases. And we just deem here that that's beyond our current scope. This is just an introductory course and we cannot do all the derivations. But if you're interested, look into the 101 on statistical physics and the kinetic theory of gases. So we are considering phonons now as a quasi-particles, and they form a three-dimensional gas inside the solid, and they can move around, scatter with each other and other impurities and electrons and whatnot. and well, not really that much of electrons usually, but mostly with the atomic cores and impurities and other phonons, if the temperature is high enough. And then this gas of phonons then transfers energy. But it's a statistical process. We have many phonons, and we have many scattering processes. So we really need to also have a treatment where we are properly taking into account the fact that we have awfully many phonons, and the fact that they behave on a macroscopic picture as statistically as they do. So in essence, what we do in this treatment is that we treat phonons as energetic particles, quasiparticles, and they propagate through the solid as a gas of particles, and here we call that as a phonon gas. And then when we apply the kinetic gas theory into this problem at hand, we find out that the phononic contribution, the lattice contribution, kappa P, to the thermal conductivity equals to 1/3 times the heat capacity of the solid times the phonon mean free path, LP, times the velocity, the average phonon velocity associated. And here, these are the parameters in question. And now this is a good equation for us because it provides us means to relate the thermal conductivity of a material with parameters that we are able to estimate, and we have already either calculated, or we can then next try to look into these at how we could estimate these values. So heat capacities, we can use the Debye model to calculate heat capacities, and that also gives us already a piece of physics, because we know that the heat capacities are temperature dependent. So naturally the thermal conductivities, the lattice contribution to thermal conductivities should be temperature dependent. And then we have phonon mean free path here that somehow relates to the purity of the lattice, how ideal the lattice is, and these things. And then we have the average phonon velocities, and we will see later on that what of different aspects affect to this. And here, for example, we see that although diamond has a very low heat capacity at room temperature, so C is quite surprisingly low. I think it's around 5 joules per mole per Kelvin, and it's not very close to the 25 Dulong-Petit value. But especially when we purify diamond, the phonon mean free paths can be increased, and especially it is the average phonon velocities that are very high due to the fact that the diamond lattice is mechanically very rigid, so that the phonons propagate at very high velocities. So speed of sound is very high in diamond. And now I'm hearing Rihanna on my mind, since diamonds were mentioned. Okay, so the kappa P, the phononic contribution to the thermal conductivity, is this. And we know how to calculate the heat capacities C, and we can now kind of estimate what are the phonon velocity Vp, because we assume that it's exactly the speed of sound in the solid. And this is quite good of a statement to make as long as we are in the acoustic branch and nearby the gamma point. So this is what we saw when we were using the Debye model already. So we can estimate now the phonon velocities if we are able to see a dispersion relation, and then estimate the thermal contribution. Lattice contribution to the thermal conductivity. And the kind of what we're still missing here is that how do we consider the mean free path of phonons, LP, and this we will just consider from a phenomenological qualitative point of view. So this is where the treatment actually becomes a little bit more complicated, because in real solids we will have defects, and it will be the defects, the lattice impurities, that largely dictate what is the mean free path of a phonon, and their treatment mathematically will not be extremely straightforward anymore. So that's where we kind of raise our hands and say that we surrender. We do not deal with that math here. In general, the phonon mean free path, LP, it's really limited by phonon scattering mechanisms. So instead of acting as a free gas, where phonons would not scatter around, they actually bunch around a lot, and that hinders the average movement. As we know, exactly as what happens when we are looking at the mean free path of a gas molecules in a gas. And let's now just introduce and discuss briefly the two most important phonon scattering processes. And the first that comes to mind and first that is most important are the phonon impurity scattering processes. So instead of having an ideal lattice, crystalline lattice, we will have defects, and the phonons can scatter out of these defects. And this is what happens. And of course, the temperature dependence of impurity phonon scattering is not very clear, because like the kind of movement of defects, we haven't discussed that at all, how that is being affected by temperature. But the kind of first approximation would be that this contribution does not depend on temperature very sensitively, because like the impurities should not depend that much on temperature. So mostly we assume that the impurities in a solid do not depend on the temperature. But that's not actually a true, because they are also a little bit dynamic in the lattices, especially when we have like not cryogenic temperatures. Another process that may play a role and will play a role is a phonon scattering. And this is essentially a nonlinear process to spoil some of the fun. And this is also the mechanism that is not very strong in diamond, due to the fact that it's mechanically quite stiff, so that the number of phonons that we have in diamond at room temperature is very low. And because we don't have many phonons, they do not yet interact with each other nonlinearly, because we just don't have high numbers yet. And usually both of these mechanisms play a role. There would also be phonon electron scattering processes, but they are usually quite small. If I remember correctly, like they can play a role with semiconductors, so that there it's the charge carriers, so either electrons or vacancies that can give rise to phonon scattering, but usually it's not the first contribution that is dominant. And let's focus first on the former mechanism and look what happens in terms of phonon impurity scattering. That what are what kind of defects happen and what happens on a macroscopical point of view subsequently when phonon impurity scattering happens. So impurity scattering rises from the lattice defects. Of course, we know that's what that means. And if you need to recap what are impurities, what are lattice defects, I really recommend you to go back briefly into the chapter 3, where we were focusing on the mechanical properties, and we will briefly introducing to you lattice defects. So there can be, for example, vacancies. So the atomic lattice is missing an atom. We can have inter or substitutional defects. So a interstitial defect is that we actually have an additional atom between the atomic lattice, and substitutional defect is that we replace a given atom with another atom. And then, for example, one example of a substitutional defect would be a isotopic change in the atoms. So, for example, with respect to my favorite material, diamond, even though we do not usually think about it, when we look at a diamond, it's not isotopically pure. The normal diamonds, that they are around 1% of atoms in diamond are actually of C13 isotopes and not the C12. And due to the fact that the mass of our atom is now different, then when we are looking at phonons, lattice vibrations, we see that this is actually an impurity. And this affects. And interestingly enough, you can actually fool around and you can tweak things, so you can purify things, materials, I mean, and you can like isotopically purify them, and that actually affects the thermal conductivity. So this can be experimentally verified that this indeed is a mechanism, and indeed this affects, and that is known. And subsequently, if you really need to have the highest possible thermal performance out of your material, you may need to end up using ultra pure materials, where, for example, you have been reducing the other isotopic contributions. So you enrich, for example, the C12 contribution in your diamond. Other types, and these are not the point-like defects anymore. We have dislocations and we have grain boundaries in our solid. And an example, like follow-up implications that come to mind looking at the list of defects here, and especially the highlighted inter and substitutional defects. If we would be interested in semiconductors, and many people are on the globe, trust me on that. If we, for example, dope a semiconductor, and this is what we do essentially when we are making semiconductor physics to happen, that decreases the kappa. So in principle, in some applications, like you are decreasing the thermal performance of your semiconductor devices because you need to dope them. And more importantly, like depending on the type of dopants, things will be slightly different. And because, and we will learn about this in our chapter 6, when we are really focusing on semiconductors, we will see that more interestingly for the physics of semiconductors, by depending on the type of dopants, what kind of additional atoms we put there, we can actually change the concentrations of majority carriers. So we can, for example, we can N-dope a semiconductor, or we can P-dope. So we can actually have majority carriers that are either electrons or vacancies. But let's not go into semiconductor physics yet, because that will be discussed in chapter 6. So here we are really focusing now more on the thermal properties, and especially of dielectric materials, because we do not consider the conduction electrons in chapter 4 in this chapter here. In chapter 5, we will look into metallic solids more, and we will look into the electronic properties. And then in chapter 6, we kind of go into treatment of semiconductors. So that there's also this kind of a little bit of a distinction between the different material types in our course. Chapter 4, dielectrics, chapter 5, metals, and chapter 6, semiconductors, in case you have not noticed. So, other types of defects, and now I'm just highlighting all of these defects, and what we can see from the list is that obviously, if you would be able to make a monocrystalline material, then it should be a better thermal conductor than a polycrystalline material. And this trend is visible if we would do the experiments and when we look at the tables of different materials. When we decrease the different defects in our material, we see that they become better thermal conductors. So that we increase the mean free paths of phonons, and then we may also affect a little bit about the phonon velocity. But mostly it's really changing the phonon mean free paths, so that the phonons do not scatter as easily from impurities when we make a monocrystalline material. Okay, next, grain boundaries, and my one-liner regarding these defects. It's really hard to eradicate them completely. And this is the reason why in practice it is actually the grain boundaries that often limit thermal conductivity's kappas of many materials, many solids. So this is the kind of where we will usually ultimately end up with. So if you, for example, we can isotopically enrich a material, we can make it isotopically more pure and such, but grain boundaries and these non-point-like defects in general, it's hard to entirely get rid of them. And here I would also like to point out to you that although we are really emphasizing a good thermal conducting capabilities here for a material, so that we are kind of looking for materials that are good thermal conductors, it's also the case that in some applications we really need thermal insulators. So that this is also sometimes what we need. a silly real world example. I don't remember, was it mentioned in Hoffman's book or in Kittel, but for example, if you would have a cup of hot liquid, let's say I'm a coffee drinker, so it would be a liquid coffee, hot one, not frozen coffee, and I would want to stir the coffee. I don't use sugar, but if I would use sugar and I would want to like stir the sugar into my cup of coffee, and if I would stir it with a diamond spoon, because like, hey, I like diamond, so I have diamond spoon at home, and since diamond is an insanely good thermal conductor, like quite instantly the spoon would be at the same temperature as my coffee, and then it would be impossible to stir the coffee anymore with that spoon. So for example, that a very simple real world example that sometimes we actually not need a material that is not a very good thermal conductor, but rather the opposite. And this is, for example, where very different kinds of ceramics and glasses come to save us, because they usually are not very good thermal conductors. So I urge and I recommend you that you would also think a little bit about possible applications, or maybe even Google around that where you need these different properties. But you kind of maybe then realize more easily that it really depends on the application at question, that what are the properties that you seek for the material to have ideally. So this is what I wanted to say here regarding this slide. And then, okay, we have this inter and substitutional defects. So, okay, here I would want to highlight again that these can really be reduced when we go to using ultra pure materials. And then essentially, how do we do this is that we could, for example, isotopically enrich a material, for example, diamond or silicon. And this is in fact what is being done when we are seeking for the highest possible performance. Now, I think I will have a discussion exercise on this or some further work, because I think it's a good example of connecting dots in terms of thermal conductivities and impurities. And also, I think it's a good exercise for us to realize that in real materials, we often also have materials that are just not isotopically pure. Because usually we kind of think when we look at a material that it's isotopically pure, but that's never the case in reality. The second main phonon scattering mechanism that we were mentioning earlier was phonon scattering, and as the name really implies, is that this contribution really depends on the number of present phonons. Because if you only have a single phonon propagating inside your material, then it cannot really scatter it with another phonons, because there's no other phonons. And due to this fact, because we do know that based on the equipartition theorem, that when we have a higher temperature, then we have a higher number of phonons. And then this implies to us that this phonon scattering process and processes, they are very highly dependent on the temperature. So what this means, that when we are at low temperatures, it's very small, the contribution is negligible, but this will dominate at high enough temperatures. And please note here that when we are saying temperature, this is just arbitrary and really depends, it's a relative value what we say here. It depends on the stiffness of our solid. So for example, for a diamond, what means low temperature and what means high temperature, the actual values are different than what they would be when we would be looking at a softer material. So please remember that this is really, it's more like the Debye temperature we are speaking here, Debye temperature, so theta and such, or scale temperature with respect to the Debye temperature. And a general trend here is that the thermal conductivities decrease when we go to higher temperatures, because then we will start having more and more phonon scattering, and this is ultimately the mechanism that gives rise to the decrease of thermal conductivity of solids. So we start having phonon-phonon scattering, and then that reduces the mean phonon free paths, and that reduces the thermal conductivity. And because the heat capacities decrease at very low temperatures, please recall the Debye model and our previous lecture on heat capacities of solids, that when we go to very low temperatures, we really have the T3 dependence. And this implies to us that solids will have an optimal temperature range. And for a silicon, I think it was around 26 kelvins, where their thermal conductivity kappa is maximized. So I'm plotting here an example figure, and this is silicon. And here we see that it's maximized at a given temperature. So the slope downwards, this is being caused by the temperature dependence of heat capacity. So please recall that the thermal conductivity kappa is linearly proportional to the heat capacity. And when the heat capacity starts going down, then that means that also the thermal conductivity starts going down. And then when we go to the higher and higher temperatures, then we start having more and more of phonon scattering, phonon-phonon scattering, a nonlinear process that depends on the number of phonons present in the lattice, and that starts decreasing the thermal conductivity. And there will be, because of these competing mechanisms, there will be a sweet spot where the thermal conductivity is maximized. And for diamond, because it's mechanically quite stiff, this sweet spot, if I remember it correctly, it's being moved towards the room temperature, and that's the reason why diamond is really such a good thermal conductor. Because looking at this value, we see that this is actually quite high, around 3000 watts per meter per Kelvin. But the fact is that when we are dealing with the room temperature, somewhere here, like we have already gone quite a bit down from the optimal value in terms of silicon. But depending on the materials, the slopes are different, but the overall trend will be similar. And before I end, I would just like to highlight a little bit more about the phonon-phonon scattering, that this current formalism that we have used to understand phonons is not really adequate at all to understand phonon-phonon scattering processes, because what we have done is that we have assumed that we have linear coupling forces between the adjacent atoms, and that gave rise to phonons. But the trouble here is that this system is linear, and that means that the superposition principle applies, and this in fact means that in this description or level of description, the phonons won't yet interact with each other. And this means that we do not have phonon-phonon scattering at all. So this is the kind of price we pay for the simplified model. That we can describe phonons, and we can describe their propagation, and we can even calculate things such as the heat capacities, and we can estimate the thermal conductivities using these kind of phenomenological reasoning. But we cannot yet calculate things, because we should really go beyond in order to be able to estimate nonlinear processes between phonons. Now, of course, in principle, we could also have phonon-electron scattering processes, but they have not been considered here at all, because usually it's negligible. Please remember that phonon is a lattice vibration, so really moving the atomic cores, and we are not interested with electrons here when we are looking at the lattice contribution to the thermal properties of solid. So I think I will stop here. I hope this was a educating lecture. And finally, in the next lecture, we will go and speak a little bit about thermal expansion, which also extends a little bit of our theme that sometimes we really need to go beyond assuming a linear system. And from the macroscopic point of view, thermal expansion is a prime example of a process that we must really generalize our system. But more on that in the next lecture. So I thank you for listening, and please join me soon with the next lecture. So thanks and bye-bye.